Good day, Chem 30s. We're going to look at topic 4, which is cell stoichiometry. So we had a little bit of practice with this already in this unit. We're going to have a little bit more here just in reference in dealing with actual cells. So in the production of elements, the refining of metals, and electroplating, the quantity of electricity that passes through a cell determines the masses of substances that react or are produced at the electrodes. We know from oxidation and reduction half reactions, a specific number of electrons are lost or gained. So we know that we have our ion of zinc, we have our atom of zinc as a solid, and then we have this electron transfers. But how many moles of that are transferred? So this reduction half reaction tells us that 2 moles of electrons must be gained to produce 1 mole of zinc. This gives us our mole ratio that we can use in stoichiometry. In order for us to be able to use electrons as part of our stoichiometric calculations, we have to be able to determine the number of moles or electrons that are used in our voltaic and electrolytic cells. We need to see how the charge is determined before we can calculate moles of electrons. So we have charge Q in coulombs is determined from the electric current, which is I, in amperes, so coulombs per second, and the time T in seconds according to the following definition. So we have a formula, Q is equal to I times T. And so our first example, and only one for this one in particular, is modern electrolytic cells may use up to 300 kiloamps of current. What is the charge that passes through one of these cells in a 24-hour period? Oops. So I wrote down my electric current, which is 300 kiloamps, and I need to convert that to amps. So what I do is I make myself up a little ratio here, and I know 1 kiloamp is 300 amps. I use unit cancellation. Kiloamps crosses off with kiloamps, and I'm left with amps. 300 times 1,000 is 300,000, so I have 300,000 amps multiplied by, I have 24 hours. I need to convert that to seconds, so then we have 3,600 seconds in an hour. 24 times 3,600 is 86,400 seconds. So I multiply that with my 300,000 amps, and I get a large value of 2.6 times 10 to the 10 coulombs. And I'm done. So we're looking now at Faraday's law. So Michael Faraday found that 9.65 times 10 to the 4 coulombs of charge is transferred for every mole of electrons that flow in the cell. In modern terms, this value is the molar charge of electrons, also called the Faraday constant F, which is found right here. We can use this number to convert electric charge as we calculate here. So we calculated the electric charge here to convert electric charge to an amount in moles of electrons. This is similar to the way that molar mass is used to convert mass to a chemical amount. So what happens is that we have that formula there, and if we use it, because Q is equal to IT, we can say our number of electrons is equal to IT over F. So we have another example here, which is what amount of electrons is transferred in a cell that operates for 1.25 hours at a current of 0.15. All right, I'm going to make some shortcuts here regarding my calculations for time, but if you have any questions about that, let me know. So my time is 4,500 seconds. I 0.150A, and F is 9.65 times 10 to the 4 coulombs per electron. So use the formula that we have just listed. Number of electrons is equal to IT over F, which is 0.150A times T, which is 4,500 seconds, over 9.65 times 10 to the 4 coulombs per mole times electrons. What happens is that all my moles cancel out. Coulombs. I'm left with 0.00699 mole. All right. Half cell calculations. The mass of an element produced at an electrode depends on the amount of transferred electrons. A half reaction equation showing the number of electrons involved is necessary to do stoichiometric calculations. So we have to have that, our electron showing. It has to be in that half reaction form. It can't be in the net reaction, or else we're not able to look at the electrons we have. Separate calculations are carried out for each electrode, although the same charge and therefore the same amount of electrons passes through each electrode in the cell. So we have just a summary here of the procedure for half cell stoichiometry. We're just going to work through some, and then you can always refer back to the summary. So in our first example, what is the mass of copper deposited at the cathode of a copper electrorefining cell operated at 4.0 ampere for 20 minutes? So we have copper 2 plus aqueous plus 2 electrons produces Cu solid. Okay. We know that my I is equal to 4.0 time is 20 minutes. That is 1200 seconds. And my Ne equals IT over F. These are the values I have. My constant for F, I get 0.0497 moles. Just move that over a bit. Like that. And I need to find out what my mass is for this. Well, is there anything else I know? Well, I know I can find my N value because I have 2 in front of there, so I need to divide this by 2. And I get N equals 0.0248. Should be 8. Oops. 248.7 moles. And then my molar mass of that is 63.55 grams per mole, which gives me a mass of 1.6 grams. Our next example is Ag plus aqueous plus an electron will produce Ag solid. To balance this out, everything already is balanced, 1 to 1 to 1. So what we do is we need to find our, what's the question? Silver is deposited on objects in a silver electroplating cell. If 0.175 grams of silver is to be deposited from a silver cyanide solution in a time of 10 minutes, predict the current required. So this one we kind of have to work backwards. We know we have our mass here of 0.175 grams. Our molar mass is 107.87 grams per mole. And we're able to find our moles of 0.001622 moles. We're trying to find our value of I. We have to predict the current required. We have I. Our time is 10 minutes, which is 600 seconds. And from there, we can use the formula, and E is equal to IT over F. And we can rearrange to find our I. So this will look like I equals F times NE over T. We should get a final answer once we're able to find our number of electrons by moving this to here. So N equals 0.0016 mole. We can use this formula here, plug our values in, And we should get a value for I of 0.261. The last example for you can get started on practice sheet 11 here is a 25.72 gram piece of copper metal is the anode in a cell in which a current of 0.876 ampere flows for 75 minutes between the final mass of the copper electrode. So we have copper solid is being oxidized to Cu2 plus plus 2 electrons. So it tells us what our amperage is, which is I, we have T, and then from that we can find our N electrons, which gives us 0.0408 moles. When I move this over, N is equal to, I had to multiply it by 1 over 2. N is 0.02042 moles. My molar mass is 63.55 grams per mole. So my mass used equal to 1.2976 grams. All right. I'm going to come back with the rest of the solution in the next part. It's only going to be about 2 minutes long, and then we will be done with this section.